now it's time to start. Okay, so good morning, everybody. Thank you for coming. Yeah, it's a great pleasure to have Professor Derrida from Collège of France. As most of you know, he's really the one expert in the statistical mechanics, especially on exact solutions for nonequilibrium systems, and also singular results and so on. And yeah, this time he kindly accepted to give three kinds of lectures on fluctuations in nonequilibrium systems. And so we will have lectures today and Thursday, Friday. So always from this time, 11. Yeah, I think we need to. Thank you for the invitation and for the big pleasure to be here in Cambridge. So, we have to do loud deviation in nonequilibrium systems. Yeah, especially today it would be rather elementary. So the first example of a non-equilibrium system that you can consider is the situation where you have a steady state. So imagine that you have a system in contact with a steady state, temperature T2 and T1. And then if you wait for very long, the system will reach a steady state. So you start with essentially any configuration. And then you characterize some microscopic configuration. The main problem with the steady state is that you don't know what is the distribution of the configuration in general, except for some particular models that we will come to see better. But usually you don't know this distribution. In contrast with the case of equilibrium, when T1 equals T3 equals T. You might be interested in because the system is fluctuating. You would like to know what is the average flux of energy through the system during time. Now, this flux of energy, in fact, you can see something when the system is close to the system. And so this is called linear response theory, and I will tell you what it says, and it's very simple. I can do the derivation, but it will take too much time if I restart from linear response theory. So, okay, so let me just say what linear response theory says. Imagine that now I am in this situation, but that I am close to equilibrium. So T1 is T2 plus delta T, where delta T is very small. Okay, so the average current, you expect that there is no current will be a function which then I call it D tilde.
coefficient, which depends on the temperature, but depends on the system, on the size, on what, whether it's a gas, a fluid, or whatever. And okay, so it's a complicated thing and it's hard to calculate. Now, if T1 equals to T, then Q so will be 0, but still, because we have the system, imagine that we have the gas here, so sometimes the particle hits the left boundary, so they exchange kinetic energy with the left, the kinetic energy with the right. So that will happen that 2 square will fluctuate. So some energy will go from the left to the right, and some will come back and forth, so you have fluctuation. And this, let's say that I think it's sigma tilde. And what linear response tells us is that sigma tilde and d tilde are not independent, and they are just related by the identity that way, and so these two quantities are the same, and this is linear response, and KB is the Boltzmann constant. And okay, maybe it will have here one 2 times later in this talk, but potentially so this is linear response theory. Now, one way to derive it is you could derive it with the usual way of linear response theory, which is used in the same context. But here there is one way to derive it, which is using the fluctuation theorem. The fluctuation theorem, and also I'm not going to show the fluctuation theorem, but I'll put it in my notes with some documents at the end I can explain. The fluctuation theorem is able.
Where?
The fluctuation theorem says that you could observe certain time so the energy which flows to the system during time so, and imagine that this time is very long. The probability that divided by the probability of for a large time, so here maybe there is a big factor, but it's exponential future times 1 over T minus 1 over T. So this is the fluctuation theorem for this. So it is there were a lot of discussions about it because it says that in general, second law tells you that Q tau would be positive if T1 is larger than T2 because energy flows from the hot to the cold. But then here it says that still there are events where it goes the opposite way and the probability ratio of probability is given by that. Now, this is true if it, as I said, that sigma tilde of these quantities depend on the system, depend on the size, on the nature of the system, but this formula is just here, there is KB1, but it's independent of the system. There are some conditions for its validity, but most of the systems will just satisfy the condition. Okay, so now if you just take this, and then you say that T1 is close to T2, so T1 is effective, and then you say that this probability here, essentially there is a maximum, the average current is maximum of the probability, so you just expand this near the maximum, so you say that here Q is essentially exponential minus Q minus delta T that time so divided by and cube minus 2 the formula which is the same, multiplication 2 by minus 2, and then and to make the ratio. So here I have assumed that I am that the cubes are small and I am near the maximum. So I write this formula, this one, I make the ratio, and I get what I said. That is, when I make this ratio and I compare to that, I get this expression. The 2 squared will disappear, and then only the linear term in 2 will survive, and then you get it. Now, in this talk, I will mostly discuss not the flux of heat, but the flux of particles. But the theory is exactly the same. So imagine that I have particle systems. So I have 2 reservoirs of particles. And the situation theorem if you can probability of people divided by probability of minus particles, how many particles went to the system. Now when I say that, I have in mind always that the time is very large, so Q does not depend on where I observe it, because I assume that essentially for large time, all particles went which enter the system left the system, except maybe the 2 ones which will not contribute at when time is very large. So and among the cases where the fluctuation theorem does not apply, systems where particles could accumulate or energy could accumulate inside the system. So you keep the system to make models which allow to keep the system not valid. But anyway, when you talk about particles, you have mu1 minus mu2 over T, okay? So T is fixed. And now I have just different densities for different chemical potentials. You can repeat the same, and then you find the average current is the tilde times V1 over V2. Where when U1 equals V2 in sigma tilde, and then we have that sigma tilde is 2T times T tilde. So again, this does not matter. It does not matter which system you look at, whether it's large, small. It is just a consequence of this equation theorem. Now, often people talk about, when you talk about this particle systems, prefer to talk about flow. Flow is, let's see, this tilde of rho1 minus rho. Okay, so then there is a slightly different formula here, which I write. A very simple origin. The sigma tilde is 2T, 1 over d over 0. And tilde. So the relation cares about how the chemical potential depends on the density. Okay, and this is the derivative of the free energy, and this formula will come back hopefully today. So what I said so far is true for the general. We have some conditions, but the system does not need to be large. The only thing is that time has to be large, so the system has reached a steady state. Now, let me talk now about diffusive system. So diffusive system is just system where we say something about how the d tilde and sigma tilde depend on the system side. And essentially, it says that if you have T1, T2, and the system side is very large, then d tilde is the average flux of T times T will be just okay. So it will be of this one, T1 minus T2 over N times D. Okay, so before I had just D tilde, now I have D of T, but the L dependence is important here. And this is called, so this is when minus T2 is here. And this is called Fourier flow. And of course, because D tilde and sigma tilde are related, then of course, so square, if you are at equilibrium, when the difference of temperature is zero, will be the sigma of T over L. And again, the D and the sigma depend on what system you look at, but they are related the same way as D tilde and sigma tilde were before. And for particles, the theory is the same. Doing the things that Q over 2 will be one when it's equal to times D, which depends on rho over N. So the system is large. Diffusive means there is an N there, and Q square means that this is sigma of 4, and this is called Q square. So there are systems which satisfy Fick's law and Fourier's law, and there are systems which don't. For example, the simplest system you can imagine here is an ideal gas. So the system will be an ideal gas. The particle will travel without interaction. Then the flux of energy from here to there does not depend on the system size because they have no collision. So there is no way that the system size matters. So if you take an ideal gas, you don't have the head. Or a perfect crystal, which is just a harmonic string, you don't have that. And there are many examples of systems which do not satisfy Fourier's law or Fick's law. In particular, about Fourier's law over the last 20 years, there have been a lot of work about anomalous Fourier's law, where people claim that the C system where here the exponent is but something else. Okay, but here all these lectures I will consider systems which satisfy this load and say that they are diffusive. And okay, there are many others. We'll see a number of examples which satisfy this load. Okay, now once you say that, now I'm going to really consider any particle. The theory is exactly the same for if you were looking at the temperature. Then you have your system, and now you might be interested in a situation where the density of the boundary are not the system of type N. With the densities of the boundary, because this boundary is here, and the boundary is O2, and the difference is not small. But the claim, and essentially lots of things I am going to say, will be that knowing these two functions, you can predict what happens. You don't need to know more. So these functions are defined when the system, when the difference is small. Now, assuming that the difference is small, I know the functions, and now I can say everything for a situation where the difference is not small, it could be arbitrary. And the idea behind is rather simple. You wait for very long, the system will reach a steady state. Maybe it's not a linear profile, but somehow, if the system is very large, in each small region here, okay, and then this small region is LGX is very large compared to 1, but the X is very big. So look at the small region. And now for the small region, the difference at the boundary is small. Therefore, the flux, so if I just consider the freedom, will be P of rho around the region X. Okay, so somehow I am a system of size L, and then here I am at the position which is LX, where X is between 0 and 1. So I concentrate near this point. Now the difference is small, so this will be rho1 minus rho2, so it's 4 of X minus 4 of X plus Gx. And for this sub-region, then the length is Lgx. And therefore, you see that 2 over 2, something which is rather obvious, is that in this one-dimensional system, this does not depend on the position. It does not depend on the position because everything which came from the left has to lead to the right. When time is very long, otherwise they will accumulate. So this is the dependence. Yes.
So dimensions, what dimensions of the X and L's? Because
L is the length.
but the X is also a length. So it's 1.
No, the X is the for the 1. Yes,
Oh.
the X is between 0 and 1.
Yeah.
So LGX is, yes.
Okay.
So this will be minus 3 of 4 times 4. And then there is a 1 over L left. And this is the average current. If I wait for the element, so let me call it G. And so the first thing you realize is that presumably all the current will be of order 1 over L to calculate the system. And this is the constant. And therefore, from that, I can get the profile easily because I will get the differential equation for rho that you can integrate. And the way the answer is the following: if you try to integrate, you get that integral from rho. If you want to know what rho is, from rho1 of 0.0 is equal to x times Lg. So in fact, you don't find rho as a function of x, you find rather x as a function of rho. Because okay, you can just invert it, and then so with the average current is the integral from rho to rho 1 of rho 4. So this is the profile, whatever system you have. If it is diffusive, you get the profile. You can get J from here, and then you get the profile from that. Okay, so this is what I have done here. I say that theory of system, rho1 and rho2 are very different, but still locally the difference is small, and so I just can express everything in terms of this D and sigma. And the story, we are going to repeat this story in many contexts. So now I want to introduce the macroscopic theory. Okay, so a version of it. It was introduced by people in Rome, but I will give you slightly more physicist version of it, macroscopic. And so it was introduced at the beginning of the year 2000 by Bertini, Gabrielli, Jona-Lasinio, and Landim. For example, the wrote in the time, but it started about 20 years ago. And okay, so typically the whole story about that is to say, okay, I have seen my history, my Derrida system. On one side, I have a reservoir density ρ2 for one, for ρ2. And I would like to say, okay, so this is one situation that we discussed maybe slightly over some other situation in the next lecture or so, but okay, so now we have talked about what is the average profile of the profile. Okay. Now I can ask, okay, I said for a profile rho A, so initial condition, or I, initial condition, and then I say there is another profile rho finite, and then I would like to know what is the probability that during time t or time tau, I observe the finite profile, given that at time 0, I have the initial profile. So I imagine I start with, I put parentheses because it's not a function of the number, but it's a function of the profile. So what's the probability that I observe this finite profile, given that I know the initial one, and given that I have a certain time here? Okay. And why can I say something about it with the two I showed you is that essentially if you go from here to there, okay, there will be some intermediate profile, but always locally it will be close to equilibrium. Although the whole system is very far from equilibrium, O1 and O2 are very different. When the system deforms itself, then essentially, locally, everywhere, we are in a situation where you have the D of rho, or the D of local rho. So you see when it deforms, the rho changes, but locally, you can apply these things again, because this small interval here is, okay, it's small when I look at it on large scale, but it's very large when I look at it on the microscopic scale. So because it's very large, I can use this formula. Okay. So now, if you want to, so now I am going to say something about this probability. But to do that, we need to make a rescaling. So, okay, so the picture you should have in mind is that in principle you have a model of the system, and at the microscopic level, okay, if you look at the density as a function of the position, so here let me say, okay, I do the position. the density looks like this. Sometimes there is a particle, sometimes it's empty, and then later on there is a particle, and then maybe there might be more particles somewhere, but essentially it's a discrete thing. And okay, and here I want to talk about profiles. So I would like to look at it at a large scale that I can talk about the density profile. The same is true, for example, if I look at time, if I look at the flux of particles or the current of particles at time t. Sometimes the particle enters the system, sometimes the particle leaves the system, so it's only delta t later. And so these things are functions which have fluctuations. So you cannot imagine that you can talk about Gaussian fluctuation. So the thing is that you want to look at the system on large scale. Now you want to introduce variables to describe your system at large scale. So you need to do a rescaling. So in the microscopic world, then you have position which is between 0 and L. And then in the macroscopic world, you like position between 0 and 1. And so the change of variable here is clearly capital X will be L. At the microscopic level, you have some densities. And there is no rescaling of the density. The raw effects you have to think of is essentially an average of this box and a certain small box where you have still lots of particles, and the size of the box is small, seen on the large scale, but it's large, so you can really talk about the density inside the box. Now, we have seen that the current will be over the 1 over. So this means that you want to introduce a macroscopic current, which should be just J infinity equals L J at position X and T. Again, this current, as I said, the true current is something like that. So you need to take a time window or something which will somehow smooth this thing. And this is really what the mathematicians do. That is, they introduce test functions which vary slowly. Maybe in one of the lectures I will show you one example. We introduce test functions which vary slowly and somehow which produce a field which is not that fast. Okay? And now you want also you have, and this is very important, you have the number of particles here is conserved. So at this level, you have 0 over equal to conserved minus dj over dl. That's true even if you have this wild behavior. Okay, so now you see that J is capital X. So J is for the 1 over L, X is for the L. So in fact, the equation will be 0 over dt equals minus J over X. Now macroscopic, but because of the L dependence, then the two microscopic time is equal to L squared times the macroscopic time. And somehow L squared saying that the system is diffusive. Because so essentially what we have is that on the macroscopic scale we have conservation law, and now I have to tell you how these two quantities, it depends on condition and T, how they vary. And the way they vary is given by the fluctuating hydrodynamics. So at the heart of this macroscopic fluctuation theory, there is fluctuating hydrodynamics that I am going to write. To prove it, you need to take some particular models where you can prove it mathematically, and at least my understanding is that for models which are more complicated, then essentially you assume that that is mathematical very general. You follow the mathematical production. Some models that I will mention, especially next time, we will see that what I am going to write about is fluctuating hydrodynamics. And what you write is that the current here is equal to satisfy 2 years ago, which is exactly what we had before. So here it's everybody depends on X and T. D will be a rho and T plus some noise. So, and if the system is very, very large, the noise is small, as you will see, and this is Fourier law that we have said that the system, the density varies slowly, so for 1 minus 4 is small, it's the derivative, this is the view of all that we have seen earlier. And this fluctuating hydrodynamics, we say that the system on large scale is described by this equation, and the noise is just a white noise in space and time. With respect to T, delta delta T minus T prime. And what is important is that 1 over X. So the larger the system is, the smaller the fluctuations are. It's very important to have this 1 over L because essentially because you have the noise appears to be weak, then somehow you can start to talk about the optimal trajectory to be possible. Okay, so this is fluctuation hydrodynamics. What is not trivial at all is that this is white noise. The system, this is a white noise, and okay, we need to prove it. And as I said, you can prove it relatively easily for some models, but I don't think there is a general. Now, the macroscopic fluctuation theory is, I think, from a physicist, it just says the same thing. Says, what is the probabilities of going from the finite during time t, going from the final, from the initial profile at time 0 to the finite profile at time t? It is just exponential minus integral over time from time 0 to time t. There is an L here, okay, I'm going to explain. Here is X and time plus the all the arguments here, 0 over the X of X and T prime. Well, divided by 2 not to all of X and T prime. Okay, because there is a double integral. Yes. Integral from 0 to 1. Okay, so this is what it is. And what you recognize here is very somehow it's exactly the same as what is written here. J plus the fixed law here. So J plus 0 prime is just a Gaussian variable. Here, square. It's a Gaussian variable. So here there is a variance here, which appears, and the 1 over n here comes here. Divided by 2 times the variance. The result gets 1. Okay. And together with this, really, when you want to use the macroscopic fluctuation theory, essentially you have this formula and you can apply it to a number of contexts. Now, with the context here, okay, in general, for general context already, what you have is that you have this plus the conservative law, 0 over t equals minus G over T. And now, depending on what you want, okay, here you want, for example, that at time 0 row of x, so you want the row, okay, so, and let's say that here, in principle, I want to sum over all paths and all points. I write the sigma because it's functional integral as well, so I don't want to insert it. Yes.
How this formula will, I mean, the limits are very large L, where they'll go to, what is happening with this?
Okay, so when L is very large, what happens is will be a saddle point. There will be an optimal path which will contribute. So it will be the capital L here is making like a saddle point. So this is why you can say in terms just on these two parameters, sigma and t. If L is not too large, then the story is more complicated. If L is not too large, then you don't have to really low. So L has to be large. In principle, here you have a kind of path integral that you want to consider, but because L is large, essentially you're interested just with the dominant exponential, then you don't need to care about that, and you have to find the optimal path. Okay, so here so there is the J and the rho are connected this way, and of course, if I want this, I would say that the rho x at 0 initial, okay, and rho with x and t is the final. Okay, so it's an optimization problem like in mechanics. The only thing is that you are field, but otherwise we can control it. Now, okay, so I think now what, so imagine I fix this in 3, and like this expression here will be so imagine that I fix the initial condition, and I could ask how this depends on the final step. So what is the probability that the rho of final x is equal to some R of x, given the initial range? Everything here are constants, the probability that I observe a certain profile given the initial condition. And this will depend on x, and it will be a certain functional of the final. This functional is just to find the optimal path. Here, what is the optimal J, the optimal rho, which are connected this way, which will bring me from the initial state to the final. And if I change the final, then it will change the function. Okay, now what I want to write is what's called, because this is just like a problem in mechanics, so I want to write what's called the Hamilton-Jacobi equation. And so this FC depends of course on the rho initial, but rho initial is fixed. Okay, so I don't write it explicitly. Of course, this function depends on rho initial, but I am interested in its dependence on the final state. And what I want to write now is just Hamilton-Jacobi equation. They are not before we leave this answer, so something in question around
Okay, sorry, and just clarifying, so this of course is large elements.
large L. So large L, so that's called the large deviation. That's for large L. Okay, essentially what you have to do, with work it's easy to do now, to do the calculation it's difficult, is to say I take it and I choose J as the row of X, which interpolate between these two, and which make the double integral here minimum, because this will be the trajectory which makes it maximum. And because there is an L in front, it will dominate all the other trajectories. The other trajectories are possible, but they have probabilities which are much smaller. So you don't need to care. So you have just to find the optimal path.
But we want to compare to the criteria.
Okay.
Large L as compared to what the criteria.
Okay, so the criterion would be that, for example, if you have a lattice spacing, the lattice spacing, or you could say L is very large, so that Fourier's law or Fick's law is valid. So you see, the Fourier's law it's only for a large enough system. So as soon as, because for the true system, of course, it will not be exactly 1/n. It will be slightly so. If L is large enough so that you can neglect the correction to that, then so now I want to derive the Hamilton vector, not to write it and to derive the Hamilton vector, but probably many people have seen that in their life. So I want to see how this function we are changing during the small time interval. So I want to say what we have T is. And now I am going to write something, which the first time I saw it is a little scary, but anyway, so it will be an integral. So it is an integral over x, v over x, of half prime of x, v of our time functional derivative of f, v over zero, time functional derivative of f with respect to r. Okay, first term, and there is a second term where sigma of r of x divided by c, and again the derivative with respect to x, x, r of x. Okay, so this is exactly what no. I'm going to explain how we can get it. Text. It's too nice to get it. So no. Okay, what's scary is a little bit because the functional derivative of capital F, but otherwise this is the derivative with respect to x, and that two, so these two quantities are the same, and the sigma and p, I hope you start to be familiar with the play an important role in this topic. Okay, so how can I derive the derivation of that? And I don't think I need more than like this. Okay, so I want to see what f, I am interested in f, the times t plus dt. So I want to take the derivative with respect to time t. So I want to see, okay, f, so So I want to see a profile at an equal which is R. Now, it is at time t, it was slightly different. Yeah, I reached the final profile at time t plus dt. So at time t, I was slightly different, and the profile was in fact R of x plus d dx plus I hope I will no mistake with the time. Okay, I did it several times, but then you become it's a t plus dt R of x, and at time t, it is just before it was not R of x, it was something else. The question is the sign here. I have done it 3 times, and I always find the plus, but even my age, you find your minus. Now, what is f of t plus dt of R of x? It will be f at time t of this different profile, because I was already there at time t. At time t, if I want to be there at time t plus dt, I was there at time t, but I have to pay a price, which was in this fluctuation theory, which I write it. Okay, A is d of R, d of R of x, okay, G of x, plus d of R of x, R of x, over d sigma of R of x. This is squared, then it is, so this is the part of the integral which we contribute, the extra part. You see, there is a part of the integral which brings me to time t, and there is an extra part of the integral which brings me from time t to t plus dt. And because this probability exponential minus f, okay, so here I have a plus, this is I was, okay. The sign here seems to be correct. Okay, so this is what I say. And then I want to find the maximum over the g of x. So this is the g of x. G of x is just the current during this long time. So really, but this is really standard derivation of Hamilton's equation. Okay, so now this is very small. So this is f of t times of R of x plus something. So this R of x is a little modified by this. So this delta, this is where the terrible functional derivative appears, the of x, and then there is g x. Let's say very sorry, because the probability is exponential minus f, so I want to make f as small as possible to have the most likely thing, and so okay, so I have this for this part, and this I have g of x plus d of R of x, that's fine, right? Yes. Divided by t sigma of R of x. And then there is a d. Okay, and here, the thing I didn't say, which I thought I should have said, is that I have an integral over x. I have an integral. I have this integral over x. Now, you see, okay, at first I think it's very easy because I want to find the minimum over J of something which is quadratic in J and linear in J. The only problem is that here it's not J which appears in the derivative. Okay, so what do? That I replace this term by J, the derivative over H and delta X over here. And then when I replace this by that, I have done an integration by part, and I have closed my eyes. Everything is okay at the boundary. You want, you can think that you are on a ring and already. So essentially, I do an integration by part. Now I have something quadratic in J, linear in J. I just have to find the minimum for each X. When I do that, I get it. And this is the Hamilton-Jacobi equation. Okay, so it's not so difficult. Just, okay, this point, I overlooked it a little bit, but what happens is that we say, this was the profile before was this, I don't know what is the optimal day, and what the price I have to pay to this action during time t. Okay, so I have to find the optimal J given the J appears here and there. Okay, here is the derivative. I make an integration by part. Now I have just J, and then I can treat all the values of X separately, and then I get. No, okay, so this is the Hamilton-Jacobi, but I have learned something more than just getting this equation. I say, okay, let me try to think in terms of the space of density profile. I am at T. I want to find the profile at time T plus dt, say, I want at time T plus dt to observe the profile R of it. Okay, this tells me the optimal profile, that is the current, because when I optimize, it will tell me what is the current at between time T and T plus dt. So somehow it will tell me, okay, exactly what was the profile I have at time T. So I can say, if I want to see this fluctuation, how did I get there? Because it tells me this part. I will get the optimal J for this optimizing here. And in fact, so it means if I want to know how the thing has evolved when I was here, then if I time T plus dt, I have the profile of X. At time T, I had the profile which was f of X plus dj over dx times dt, with the j here, which is explicit, minus d of r prime, plus c of r, d over dx delta f over delta r of x. So if I know the cloud deviation function, which we see that there are some situations very small, then I can tell exactly how the system went up in this situation. I can, because if I know it here, I know it there, and then I come back, and so I get the good trajectory. Okay, now I am almost finished. I have almost finished what I wanted to say. The last thing I want to say is say something about this Hamilton-Jacobi equation, which is there. And I'm going to look at the simplest case that you can imagine, which is the system at equilibrium. It will take 2 or 3 minutes. Now, okay, here there is a theory, but essentially the theory applies when I am at equilibrium, that means that O1 equals O2. Okay, the 2 are the same, so the system will be at equilibrium. And at equilibrium, everything, you know, I know the Boltzmann weights, I can calculate everything. And in particular, I can show that if I define the free energy as a zero, okay, so let me say how it is defined. Imagine that the system is large and I have ZL of n particles, so this would be the particles might interact and whatever, this will depend essentially also on temperature, but I just want to discuss that, how it depends on the number of particles. So when the system is large, this will be L of F of L over L. So if I have a certain density, the system is expansive, and I have a F is essentially the free energy to a sign of a factor beta or whatever. But okay, when the system is very large, the partition function, when I have n particles of a system of size F, there is a kind of free energy per partition F. Now, it's easy to show that F equilibrium probability of observing a certain density profile, our test will be just given by integral from 0 to 1 of F of our test minus F of the rho at the boundary. So this is an equilibrium property, and to get it, okay, we're not going to do the calculation in detail, but the main idea is that you have a very large system, and so you have N1 particle in the first box, N2 particle into the second box, N3 particles in the last box. I have a system of size L, then the probability of that will be Z L of L1 plus L2, and I thought it would be L over L of L1 times L over L times L2. Essentially, when the system is very large, you can neglect the boundary effect, so you have just a product of that, and then when you write that the Z is of this form, you get it. Now, okay, so this is an equilibrium. This means that it's time independent. So now let's put this expression into the Hamilton-Jacobi equation. So delta X over delta R is just S prime of R. And now to derive it, T over dx of that is just F double minus R. So you take this, you put it there, and you find that because it's an equilibrium, it does not depend on time. And what you find is, you find that F double prime over R, well, sigma of R divided by 2 dx. In other words, you have the sigma and d. Remember, we talked about them number of times during the talk. Okay, sigma and d sigma of d are related by some equilibrium property. This is the strain, F is the strain energy at density rho, and this is the Pythagorean derivative, and essentially it goes up to maybe 1 over x, what's called the compressibility at equilibrium. So if you know, if you have a system and you know its energy, essentially you know the relation between D and C. And so there is a single parameter to know. Okay, so let me start. Thank you. If you have questions, then I'm very happy to repeat that.
Thank you very much. We have a minute lecture. Any questions, comments?
Well, so I guess I've got this about the Hamilton-Jacobi equations. So I guess I somewhat missed where we did the minimization over the currents, all currents.
Well, okay, so at some stage, I had something with T over the X times the delta F over the other face. plus J equals D of prime square the velocity. And I say I want to minimize that with respect to J. But that's easy because quadratic is J. Okay. Like the difficulty. So the only thing is that this is a derivative, but you make an integration by part. So you replace this by minus J D over here, delta S over delta of this. Because this is where the not so pleasant object appears. And now I have J Z squared. I find the minimum of the quadratic of the parabola.
I think I learned some Hamilton-Jacobi equations when I learned analytical dynamics.
Yes, but instead of being a function just of a trajectory, here is a functional of the function. Okay, depends on how. Depends on how. I don't know.
But, so the system is not really Hamiltonian. We have some, in analytical dynamics, we have Hamiltonian, so there's an equation of motion of Hamiltonian, and then it is reformulated into the form of Hamilton-Jacobi. But now we are not speaking.
No, but if you start with, if you start with the function, yeah, it's minus L integral with X and T of the integral J plus D of L over or after prime and CD2 CDR. Fine. So first it's a function. Okay, it's a function of the shape R. Okay, but R plays a role in visual dynamics of T. Now J, remember dj over dx is 0 over the T. So somehow the J which is here is like the Q dot that you are using. Because somehow it contains the derivative of sorry, but it contains, okay, because the over dx is a little more, slightly more complicated. But in spirit, J contains the derivative. What did I find? Yes, okay, there is a minus sign. In spirit, J contains the derivative of the density, and all the rest depends only on the density. So Q is R is the generalization of Q, and J somehow is the generalization.
When we because of this condition, we can think of this system as a kind of Hamiltonian.
Yes, yes. So it's like a Landim.
It was mentioned somewhere that you didn't regard, but where again, well, because if we look at the SPL, the prime relationship of sigma and dr, you probably can write it also for that cat.
Yes, that's very what we do also.
Later, you can write expression and read expression.
Yes, that's what we, yes, we see examples for that. Yes, yes. But today I did not look at a specific model, but that's true for any system. And so you might have a lattice gas or the continuum, so provided that they satisfy Fourier's law, they are diffusive, so that they are diffusive, then you have this palette. You don't need, but okay, diffusive system, it's not so easy.
And a quick question about terminology. At the beginning, you were thinking about the name equation. It looked like it was just a fixed law with a random pool. Why you call it hydrogen?
It's large scale, okay, hydrogen in the meaning of large scale equation from the very simple element.
The system should be diffused in the story, right?
Yes, yes, and
Okay,
okay, I will not think I will talk about non-diffusive system here because but,
Yeah, that's fine.
yes.
Other questions, comments? If not, this time.